Howdy, today I'll be demoing the single cycle processor and its functionality, and I'll go through the main module file and my re-implementation of the sign extender. My initial implementation was incorrect, so I want to go over this. And yeah. Okay. So first of all, sign extender. My initial implementation, I did not even use a control signal, the LEGv8, and I literally just pulled the, based on the instruction type that I found in the textbook. I just pulled the in the BTAP instruction. I pulled the 6 bits, and if there were there's only 2 cases, either this or this. And in that case, we have a branch, and then we would set our output bus with the immediate address or the branch address, and then we would sign extend the most significant bit of that for the next 38 bits. And in terms of a conditional branch, we had 3 different cases, although I could have simplified this just by putting question marks. So in this case, now we just pull the conditional branch address, which is from the 5th bit up to the 23rd bit, and then we go ahead and put that in into the output bus, and then we extend the most significant bit, which in this case is 23. All right, so D type, and the D type, these are the load store instructions, but there are quite a lot of these. So we have 1, 2, 3, 4, 5, 6, 7, 8. And yeah, so these are the 11 bits. And they're quite similar, but they're based on the size of the register that we want to transfer. But the sign extensions will always be the same. Bits 12 to 20, and then we sign extend bit 20 for 55 bits. And then I also added this BN block. And here, if we didn't meet any of the criteria, we just sign out all zeros. And in my new implementation, I actually did it correctly, and I used the LEGv8 2-bit input, and it made life much easier. And so we just I also included the I type, so that was just the immediate address, bit 10 to bit 21, and then we just extended with zeros. And I think I pulled this off the eCampus page. And yeah, so else if in case of a conditional branch, we do from bit 5 to 23, B type, same thing. And yep, branch, same thing. I could go ahead and add something like, well, I already did else, so yeah. The reason I did this right here, else, is because the branches just don't care, you know, like in the case of branch, our ALU is not even going to be used, so we don't care about it. It will not be used. All right, now I'm going to go ahead and demo my module. Single cycle processor. All right. So this is the one we had to kind of change around a little bit and play with. Firstly, we had to implement this mux. So this mux is so yeah, register 2 location mux, So this is when we're pulling the instruction from instruction memory. And so in the case of like store, load, R type, branch, conditional branch, we're going to be having to implement this mux. And so this if statement is phrased so when this control output from here, if we get it to 1, then we do RD, register D, else register M. And then after this, I think we had to implement this mux as well. This for the ALU. This. Yeah. Okay. So ALU immediate register choice. The ALU source is high. We pick the sign extended 64 bits. Else bus B. Bus B is just the register 2 data. So let's say when we're doing an R type instruction, we're going to need that for on a store. We're going to need the address. So that is when we will be picking 0. Else pick 1 for the sign extension. And I'll throw that into the ALU. And then this last mux, this is for so this mux is memory to register. And if it's high, then we just pull the memory out. Else, we just take the result from the ALU. This data path right here. If it's low, it's high, we take the data read from this data memory, and then we go ahead and send that into our write data register. Now to go ahead and demo this. So I actually implement, I'm not using Bravado Xilinx. I'm actually just using iVerilog, which is on Linux. And I wrote a text file for all the modules that are required. So ALU control, data memory, instruction memory. This was provided. XPC, register file, sign extender, single cycle control, single cycle processor, and then our test bench. All right. Processor. Module list text. Now all tests pass, and our PC logic looks to be correct. 4, 8, C, which is 12, and we branch +4, +4, branch +4, +4. Oh, yeah, so we branch back, +4, +4, +4, branch. All right, yeah, so PC logic is correct. I was having issues with this, and it was just down to my sign extender. I did not implement the shift. Sign extender. Oh yeah, so my next PC, I did not implement the shift left by 2, so we're just adding 4 zeros. And that led to some problems in my next PC, but Looks like I implemented all the modules correctly, so I can go ahead and now finish this. And I'll go ahead and pull up the waveform. Test. Spell that correctly. Oh, wrong file. So here's a unit test. So that's a lot of green and red, but this is the implementation. And yeah, all tests passed. So thank you so much for watching.